David Turner notes that while quicksort is often cited as a program which defies structural recursion, it performs the same sorting algorithm, although not with the same memory usage pattern, as building a binary search tree and then flattening it. The irony is completed by noting that the latter sorting algorithm is the archetype of a structural recursion in Rod Burstall's development of the concept. Binary search trees have empty leaves and nodes labeled with elements which act like pivots in quicksort. The left subtree stores elements which precede the pivot, the right subtree elements which follow it. Surely this invariant is crying out to be a dependent type. Let us search for a type for search trees. We could, of course, define binary search trees as ordinary node-labeled trees with parameter p giving the type of pivots. We might then define the invariant as a predicate, implement insertion in our usual way, and prove separately that our program maintains the invariant. However, the joy of dependently typed programming is that refining the types of the data themselves can often alleviate or obviate the burden of proof. Let us try to bake the invariant in. What should the type of a subtree tell us? If we want to check the invariant at a given node, we shall need some information about the subtrees which we might expect comes from their type. We require that the elements left of the pivot precede it, so we could require the whole set of those elements represented somehow, but of course for any order worthy of the name, it suffices to check only the largest. Similarly, we shall need to know the smallest element of the right subtree. It would seem that we need the type of a search tree to tell us its extreme elements, or that it is empty. From checking the invariant to enforcing it, assuming we can test the order on P with some less than or equal, we could write a recursive function to test whether a tree is a valid search tree and compute its range if it has one. Of course, we must account for the possibility of invalidity, so let us admit failure in the customary manner. The guarding operator bracket allows us to attach a Boolean test. We may now validate the range of a tree. As valid is a fold over the structure of tree, we can follow my colleagues Bob Atke, Neil Ghani, and Patricia Johan in computing the partial refinement of tree which valid induces. We seek a type BST from stRange to set such that the BST is a tree which is valid, and we find it by refining the type of each constructor of tree with a check performed by the corresponding case of valid, assuming that the subtrees yielded valid ranges. We can calculate the conditions to check and the means to compute the output range if successful. We thus obtain the following refinement from tree to BST. Attempting to implement insertion. Now that each binary search tree tells us its type, can we implement insertion? Rod Burstall's implementation is as follows. But we shall have to try a little harder to give a type to insert, as we must somehow negotiate the ranges. If we are inserting a new extremum, then the range will be wider afterwards than before. So we have the right type for our data and for our program. Surely the implementation will go like clockwork. The leaf case checks easily, but alas for node. We have a BST for some ranges L and R. The then branch delivers a BST of one type, but the type required is BST of another type, so we need some theorem proving to fix the types, let alone to discharge an obligation. We could plow on with proof and coughing push this definition through, but tough work ought to make us ponder if we might have thought askew. We have defined a data type which is logically correct, but which is pragmatically disastrous. Is it thus inevitable that all data type definitions which enforce the ordering invariant will be pragmatically disastrous? Or are there lessons we can learn about dependently typed programming that will help us to do better?